So what we're going to have is we've seen this already before. We had y equals f of x and theta. This is kind of the general formula that you have plus error. Okay. Now, that's the, yeah, go ahead and take the notes. Sorry about that. I didn't give you the copy of the notes. So that's what we do in linear regression. We study a model of that form. And you saw in some of your examples that this might take something in the form, example A would be y equals theta 1 e to the theta 2x plus error. Okay, that's a possible model. Now that's not linear in theta 1 and theta 2. Okay, which is the theory we use to use the least square estimation of the parameters. So we don't have that. So what you get is that what you did before, you tried to do this. You took the regression function. So this is the actual model. Okay, plus error, right? And this is called the regression function. So in this example, the regression function, there's only one regressor, single regressor x. So it's really not a vector x. It's just, well, not a vector regressor. It's just x equals x1. Okay? There's only one regressor. I didn't make it clear what this arrow was. It's just all the x stuff. Okay? And then there's all the parameter stuff. So this is a regression function. If I actually write the regression function equation, you might just say, well, just drop that little epsilon. Who cares about that, right? Let's just drop that little epsilon in the regression equation approach and just say, right, y equals theta 1 e to the theta 2x. Then this is not linear in theta 1 or theta 2 either, but I can transform that equation to be linear in theta 1 and theta 2 as follows. I take the log of y equals log theta 1 plus theta 2x, and now that's a linear function of x. And also, nicely, that's not really what's important, though. What's important is that it's linear in the parameters theta 1 and theta 2. So this is equal to, this is linear in the parameters log theta 1 and theta 2. Okay? So therefore, we talked about making a transformation to linearize the equation. You can do that. On the other hand, if I go back and consider what happened to the epsilon, I find that I can't take the log of a sum like that, so I don't get plus epsilon. So what happened to the error? So y prime, so if I put y prime equals log y, okay, then y prime equals log theta 1, I won't give it a new name, that parameter, plus theta 2x plus error prime is a new model, but error prime now, then I get this, all right? But because I don't have any obvious relationship between epsilon and epsilon prime, what we can say is this: if epsilon has mean zero and constant variance, sigma squared we call that, then in the transform model, epsilon prime will not have mean zero. In other words, it's, and will not have constant variance. So where you just destroy the additive property of the noise. In other words, if you had the good noise, right, but with the wrong kind of regression function, then after transforming it, even though you get the good kind of regression function after transforming it, you get the wrong kind of noise. And it's not even mean zero noise. Okay? That's the problem. So now you're missing a term in the model. What are you going to do about that? How are you going to correct for that? What's another example? B. Same kind of thing going on. Y equals theta 1x over x plus theta 2. The author is going to introduce this regression function in one of the examples in the chapter, nonlinear regression. This is chapter 12. It's not really a difficult chapter. That's why I'm going to do it, but I think it's very interesting. Okay, it's a good precursor to some other chapters. So I like it better than 10. Instead of just jumping into chapter 10, I like chapter 12 better. And it kind of leads you up to chapter 10 a little bit, okay, and also leads you to chapter 13. So I like this chapter 12 as a good kind of compromise chapter where you get to revisit the issues in regression versus nonlinear regression. So let's try this one. In chapter 12, the author introduced some Churomycin data, which is some kind of, has to do with chemical kinetics or something. Let's see, what does it actually have to do with? Maybe some people would understand what that actually means, what he's talking about here. Model for chemical kinetics to relate the initial velocity of an enzymatic reaction to the substrate concentration X. Like, I know what that means. Okay. The velocity of the initial velocity of an enzymatic reaction. Well, I guess there's an enzyme, all right, and there's some kind of reaction going and the rate at which is proceeding initially. That's your initial velocity. And then there's some kind of substrate. I'm not sure what the substrate is. Concentration, is that the enzyme or the other stuff? I don't know. Anyway, I don't know enough chemical kinetics or chemistry period to know what that means. We'll have to wait till Shane comes back to tell us. Okay. He's a chemical engineer in the house. Okay. So this is the model, though. So this is the velocity, and this is X is the concentration of the substrate, which was in parts per million, so it could be over 1. Okay. And this velocity was counts per minute. Anyway, so counts per minute is how much it's changing. Okay. Counts per minute, then you're looking at basically how the counts per minute are changing each minute, right? So that's the initial velocity. Sounds like an acceleration. But they gave counts per minute. I guess they call it velocity in that chemical kinetics. Okay? So you have to know the units in chemical kinetics. But anyhow, there's your equation. Suppose this was the model, okay? Somehow theoretically derived. Then is that linearizable in the same way that this was? Okay? The author tried to make some kind of point about an equation, the regression equation being intrinsically linearizable versus the model equation being intrinsically linearizable. I'm saying that this model equation is not intrinsically linearizable because I can't deal with the epsilon. Okay, the regression equation is intrinsically linearizable because I can linearize the equation. Okay, to get an expression by transforming the variables. I only had to transform y, but by transforming y, I get, and by transforming the actual parameters too. Okay, I get an expression which is linear in the parameters, in the new parameters. So the regression equation is intrinsically linearizable. He doesn't make it real clear which equation he's talking about, okay? But I think this is clear, okay? Now, this is your model equation. Is the regression function equation, is that linearizable? Yes or no? You're nodding yes.
Yeah.
Why? Because you said so in the book?
Well, Kellis Metten is the one that came up.
Oh, you knew chemical engineering too.
Well, biochemistry.
Ah.
So I know it in a biochemistry sense.
Cool.
And so, yeah, the greater the concentration, the faster the reaction goes with the enzyme.
Okay, excellent. Okay, so you know that this one is linearizable by what method? What you can do is because you want to use the fact that you can't divide easily by a sum, but you can divide by a monomial termwise, right? So you're going to flip this, get the regression function equation. Is now y equals theta 1x over x plus theta 2. Now flip it, and you get 1 over y equals x plus theta 2 over theta 1x, which now I can divide through, which is 1 over theta 1 plus theta 2 over theta 1 times x. So now that is linear in the parameters. With the transformation of the parameters, the new parameters are 1 over theta 1 and theta 2 over theta 1, but that's okay. So this transforms the regression function equation, not the model equation, is linearizable. Okay? But again, the conclusion will be the same. If this epsilon, the conclusion, I'll say the same thing. But I'll just go back to this statement here. If epsilon has mean zero and constant variance in the model equation, okay, in the original model equation, then in the transformed model, epsilon prime will not have mean zero and will not have constant variance. What's epsilon prime? Well, epsilon prime will be introduced by y prime. I'll put y prime equals 1 over x, 1 over y, and I'll get the transformed model as y prime equals 1 over theta 1 plus theta 2 over theta 1 x plus epsilon prime. This is a transformed model. Because you still have to have an error. You're not going to fit exactly the data to the equation, right?
Should that be like a 1 over x?
Oh yeah, it should be 1 over x. Sorry about that. So I do need both 1 over. I need an x and y and a y prime. Sorry about that. Forgot to get the x prime in here. X prime equals 1 over x. Yeah, there's two things that are being changed. Forgot my theta 2 over theta 1 with a 1 over x. Okay? Excellent. So not only is y being transformed, but x is being transformed in this case. Good. So there's a natural example where I can linearize the regression equation, but in the new transformed model, epsilon prime is not going to have the good properties. I should do a couple more examples before we go on. Let me do one more example. This kind of relates to a later problem in the chapter 12. I'm going to ask you to do 12.8. And I'm going to do example 12.2 in detail. The model 12.10 relates to what I'm going to show in the next example. Oops, that guy got turned on. How did that happen? Okay. Suppose I have example C. Let's put y equals theta 1 minus theta 2 times 1 minus theta 3x plus 1/2 theta 3 squared x squared plus epsilon. Is that a linear model? Or is it nonlinear? Looks nonlinear, but...
We're talking about in the thetas?
Yeah, well, in the thetas it's nonlinear, but are there transformations of the thetas so that it's a linear model? Are there transformations so the whole thing is linear, basically? In other words, and I still have a good epsilon. assuming that this epsilon has mean zero and constant variance. So we'll just multiply it out in combined terms. It looks like a polynomial model to me. This just looks like theta 1 minus theta 2 minus theta 2 theta 3x minus, excuse me, plus theta 2 theta 3x minus 1/2 theta 2 theta 3 cubed, theta 3 squared, x squared plus epsilon. So you just rename the parameters. Here you have theta 1 minus theta 2 theta 3, and theta 2 theta 3 squared. Well, that's just three independent parameters again, obviously. So then you just rewrite this as beta naught plus beta 1x plus beta 2x squared plus epsilon, with, beta naught equals theta 1 minus theta 2. Beta 1 equals theta 2 theta 3. And beta 3 equals theta 2 minus 1/2 theta 2 theta 3 squared. So what I do is I fit this polynomial model, and then I just solve for the thetas in terms of the betas. So those would be my estimates of the thetas. So I might not get unbiased estimates of the thetas, but still, they'll be, decent estimates. Okay? So there wouldn't be any more work to do. I'll just do the regression on the polynomial regression, and then I'll find the betas, and then I'll find the thetas by backwards substitution. All right? It'd be fairly simple, right? I mean, I guess I have to solve these three nonlinear equations for the thetas, but it's linear, okay, after transformation of the parameters. That's the point. Okay. And then I think I have one more example just to close this thing up. On the other hand, if I had y equals theta 1 x1 to the theta 1 x2 to the theta 3 times 1 plus delta, where delta was some random variable, let's say between minus 1 and 1. In other words, the 1 plus delta wasn't going to be negative ever. Okay? Delta small. Okay? Then this one I can take the log transform. I get log y equals log theta 1 plus theta 1 log x1 plus theta 3 log x3, x2, excuse me, what happened? I had an x2 and x3. Theta 2 log x1, theta 3 log x2, plus log 1 plus delta. Okay. Now that is potentially a good linear model in the transform variables where, yeah, that's right, where the transform variables are log y, log x1, log x2. Then I've got an intercept too, right? And I've got transformed parameters as well. The log theta 1, theta 2, and theta 3. Pretty simple to deal with. And then I've got some error here. If epsilon equals log 1 plus delta has mean 0 and constant variance, even if it doesn't have constant variance, I probably could deal with that with the weighted least squares or something. Then all is well. Then we actually have then the transform model is in fact satisfying the standard assumptions. So if you had a multiplicative error, then after you take the log, you can get an additive error. Of course, you might still want to know whether the additive error now is normal, but at least you're in the ballpark. So if you actually knew you had multiplicative errors in a multiplicative type expression like that, then you could get the right business. Okay, so that's all the examples I want to show, showing that you have to deal with the epsilon in general. So we're going to illustrate that with the next example. So this Pyromycin example, okay, where this is going to be the model equation. So what am I going to do to estimate theta? What I want to do is take you through a review of what we actually did for the windmill data. Remember I showed you how the author made an error and he should have gotten alpha equals negative 0.83 or something instead of negative 1 when he fit a power beta 0 plus beta 1 x to the alpha to the response. Okay, so there was a nonlinear regression equation. Okay, and I want to go through the calculations of actually how you would have done that because you're familiar with that one a little bit. Okay, familiar with what went on, and I want to actually develop the Gauss-Newton procedure by using that example because you're somewhat familiar with it already. Otherwise, you're just going to be hammered with a bunch of equations. So let's go back to that one. Gauss-Newton procedure. Gauss-Newton procedure. For estimating theta. Okay? A vector. Okay? Of parameters. Theta equals, I'll just call it theta 1. I won't put a theta 0. Theta 1, theta 2 up to theta p. We're just going to denote it this way. Okay? Because it's not necessarily, intercept doesn't necessarily have any meaning now. Because I'm doing a nonlinear function. What's an intercept? You know, there may not be an intercept because it's not a linear function of the thetas. Okay? Or not a linear function of x either. Okay? It's just, so the idea of an intercept kind of goes away. Okay? I just note that. And recall our method for calculating. I'm going to do a more streamlined method for calculating the alpha in that windmill example, actually. I'm going to streamline that method. And his was kind of clumsy, actually. Okay? In Chapter 5. A little bit, based on what we have here. So if you would rewrite Chapter 5 a little bit, I think it might not hurt. But it's not bad what he did there. It's equivalent pretty much to what we're going to do. But, so if we're calculating the power alpha, and actually the others too, in the nonlinear regression function, as well as the beta 0 and the beta 1. But I was more interested in figuring out what alpha should be. In the nonlinear regression function, f of x beta 0 beta 1 alpha equals beta 0 plus beta 1 x to the alpha for the windmill data. Example 5.2. Okay? Actually, I like for a first time through, actually, I'll take it back. Example 5.2 was written just fine, but it was a little hard to follow. But, let's clean it up here. Okay? So, somehow we took initial values of beta 0, beta 1, and alpha. And that's going to be a little bit different in every problem. How are you going to get the initial values? In this example, it was, well, okay, I'll just pretend alpha equals 1 to start with the simple linear regression, okay, and then find the betas. Okay, but in general, you might have a little bit different method. Or you might be kind of far away. You might not even have a good initial guess. Okay, you might not have a good initial guess at all, and you just apply. And then there are numerical methods where you let's say have a crummy initial guess and try a couple runs of some other method to get you close. Okay, method of steepest descent, so-called. Okay, will maybe get you to a close thing. And then you use a different method after that, after you got a decent initial guess. All right? And then you might use the Gauss-Newton procedure or something else, which he's going to mention in the text. All right, so in our pure Meissen example, it's going to be a natural way, and that is to actually take this transformed equation here and solve for 1 over theta 1 and theta 2 over theta 1. That's obvious, and that's going to give us an initial guess for theta 1 and theta 2. So when you can linearize in this way, linearize the regression equation, not the model, but the regression equation, then that'll obviously give you a way to find an initial guess. Here, that wasn't so easy to do. Okay. So we just took, but it was close enough. It looked like simple linear regression. We just use that. Okay. So you started with this. Call these initial values guesses or whatever you want to call them. Beta. I'm going to use the parentheses. The subscript is going to be for the actual parameter names, but then parentheses for initial guess or second iteration and so on. So this is going to be the iteration number in parentheses. So not to think of it as a function, but that's an iteration number in my notation. He uses a superscript, but I don't want to get into superscripts. When I get to Excel, I can't use them, so I'm just going to use this. Okay. So what did we do next? Then we said, okay, then I used the first order Taylor approximation. Then I said, I'm going to expand the function. I'm going to think of x now as a fixed parameter. I'm going to expand the function in terms of the parameters. This is approximately equal to f of x at beta 0 initial value, beta 1 initial value, alpha initial value, okay, plus I have to use the partial derivatives of f with respect to the parameters, partial of f with respect to beta 0 times beta 0 minus beta 0 at 0, okay, plus partial of f with respect to beta 1 times beta 1 minus beta 1 initial plus partial of f with respect to alpha times alpha minus alpha naught. Okay? This is a fact. And now what I'm going to do is I'm going to cheat and I'm going to put the minus sign here and just put approximately equals over here. So I'm just going to put this to the other side. Okay, so I'm going to put like this. That's not really cheating and saying this way. This is just a different way of writing the Taylor series. Okay, the increment in f as a function of beta 0, beta 1, and alpha is written like this. It's the gradient of f inner product with the increment of the variables. Okay, so x is just a separate parameter now. Okay, just sort of going for the ride. So I have to take the derivatives with respect to the parameters. And then these are evaluated at x beta 0 of 0 at the initial point. Okay, so all these are evaluated there. Okay, at the initial data, initial guesses. At x and initial guesses and so on. Okay, so what's that going to do? I want to figure out, so I can actually plug all those things in, so I actually know what these things are. I know what these DFT betas are. Let's go ahead and look at that. What are the derivatives? That I can easily calculate because I have the regression function given to me. So I have df d beta 0 is equal to 1. Okay, df d beta 1 is equal to x to the alpha. Okay, and what's df d alpha? That was the nasty one. That was d by d alpha. Beta, I can leave the beta 0 off. Beta 1 e to the alpha log x. Okay, that's how you write x to the alpha. And now, log x now is fixed. It's just a fixed number. Okay, alpha is the variable. Okay, So e to the 2 alpha, e to the 3 alpha, or something like that. That's the function. It's a function of alpha. So you simply get beta 1 going for the ride, a log x coming down, that's the constant, and then e to the alpha log x back again, which is beta 1 log x, x to the alpha. Okay? So that's the third derivative. I mean, the third derivative I have to compute. Okay. So now I'm going to evaluate those at all these. So this becomes, therefore, equal to, when I evaluate them all, what does it come out to be? It becomes 1 times beta 0 minus beta 0 naught plus, now I have to plug in the alpha equals alpha naught, x to the alpha naught times beta 1 minus beta 1 naught, plus, now I have to plug in the alpha naught and the beta 1 naught here. This is all going to be plugged in at the initial. So this is plus beta 1 naught log x, x to the alpha naught, and then times alpha minus alpha naught. Okay. Okay. Now these are the increments. These are the increments in the parameters. So just underline these, or take note of these 3 increments in the parameters. And I can think of those as parameters themselves. Okay, that I'm trying to estimate in order to get the next value. In other words, I want to take my beta 0, 0 plus this, and I get my next value. Okay, so I want to estimate this increment. To estimate. Okay? To estimate. I already know what the beta 0, 0 is. Okay? And this is to estimate. And this is to estimate. These. I know what this is. This and this. All this other stuff I know. And of course I know what the initial guess is too, but I want to estimate the increment. Then I'll just add it to my initial guess, and then I'll have the new guess. Right? Alright, now how am I going to estimate those? Well, this looks like a regression equation. Right? You just have a variable 1, you have a variable x to the alpha naught, and you have a variable beta 1 naught log x, x to the alpha naught. That's exactly what we did in chapter 5, pretty much. Only we dropped off all this other stuff, it looks like, because I'm trying to unify the approach. So, and what we have here, though, is not y equals that. This looks like the error, right? This is the fit, the initial fit. And here's a regression function, which we might think of the actual y itself. It's actually y plus error. So, assuming that, so this is like an error here. So what I'm going to do is I'm going to regress E naught, which is y minus the initial fit. Minus, let's call this minus f naught, where f naught is the initial fit. I'm not putting in all the parameters, but it's going to be equal to f of x, depends on the ith observation. Beta 0, 0, beta 1, 0, so alpha 0. So in the case of the windmill data, this simply was the linear regression model, beta 0 hat plus beta 1 hat, x. Okay? That's what f0 is. It's just the predicted value for the simple linear regression. Now take the residuals of that simple linear regression and regress those on these 3 variables. 1, x to the alpha naught, and beta 1 naught log x, x to the alpha naught. This is the third variable. Okay, regress these. Regress E naught on the following 3 variables. On Z naught equals to 1, in this case. Z1 is equal to x to the alpha naught, and Z2 equal to beta 1 naught log x, x to the alpha naught. So some of the betas and the alphas might come in here, a little bit. Okay, that's fine. So those are the 3 variables. Without intercept, with no intercept, per se. the intercept is carried by this one variable, obviously, but there might not be such a thing in other examples. All right? Per se. All right? So, and then you obtain coef 0, coef 1. I'll just call them these ways to indicate that I'm going to get the slope coefficients in the multiple regression model, right? You get 3 slope coefficients, and those are your estimates of beta 0 minus these increments. Beta 0, 0, beta 0 minus beta 0, 0. So too many zeros in there, but okay. So therefore, these estimate the increments. Beta 0 minus beta 0, 0, beta 1, 0 minus beta 1, beta 1 minus beta 1, 0. So in one fell swoop, you actually get the updates of not only the betas, but also the alpha, which is different than what it was in the windmill example, because there, what you did is you found a new alpha, and then you had to do a simple linear regression, again, to figure out the new betas, then you had to plug it all in. And you had to if you look back, you actually had to do 2 regressions at each iteration. Here I'm only doing 1 regression at each iteration. But I have to create all these variables. I have to create more variables, but that's a triviality. Okay? So you actually save a little bit by this more streamlined approach. But this is the Gauss-Newton approach. Okay? So I can do this instead of with beta 0, beta 1 alpha with any thetas. Theta 1, theta 2, theta 3. Okay? So I'm just getting then your new, therefore then you get your new updated thing. So the beta 0 of 1 is therefore equal to beta 0 is the coef 1, coef 0, the slope parameter that you got from the output, okay, plus your old guess. All right, so you're getting increments to the old guesses. All right, and then just adding them up and getting a new one. Beta 1, 1 is therefore coef 1 plus beta. And I didn't actually go through this procedure this way with the windmill data, but I'll do that for next time. I guess maybe just to check everything is okay. Beta 1, 0 here. Okay? Is your guess. And alpha 1 equals coef 2 plus alpha 0. Okay? So those would be your updates. And then you would go ahead, and you're all done now. But now now what you'll do is you'll recompute E0 and call it E1 by putting those parameters into this fit function, into the regression function. And that'll be the fit 1. So then you'll then take E1 equals Fy minus F1, where now I put in the 1s here in the iteration counter. Okay, so now I have those. And this is 1 now, so I have to recalculate F1. I also have to recalculate these guys now, because now I'm going to put the 1 in here. Okay? These formulas are fixed for what the variables should be, but the parameters are coming into them, so I have to update. Regress E1 on these. I'm not putting in an update counter on the variables because I get tired of doing it. Okay? All right, I put it in the formulas. Okay? So, there you go. Now you just do it until it converges. What does convergent mean? Let's have a look at the program. Let's look at, I put this on the website. It's also in these 9 pages of Excel printout in your handout. Okay, it's called Example 12.2. Okay. I know it's kind of a quick job, but let's see how this works. I also put it on overhead slides, but I thought maybe this would be a little bit... I'm going to have to go faster now, so let's just look at it this way. Okay, what's the first thing I do? Let's see, I should probably make this smaller so it's easier to read. How do I do that? Some way. Okay. So I can only see one page at a time, maybe. Okay. All right. Can you read? Oh, I need to turn all the lights off. Is that okay? All right. What I do is I took, since I mentioned the Puromycin data had this model. It's not easy to write down the model in Excel because you can't see the theta 1x over x plus theta 2, but I wrote it down on the board before, so you have it in your mind's eye. That's what I have. Y equals theta 1x over x plus theta 2 plus error. So your regression function is theta 1x over x plus theta 2. Okay? And I'm putting theta with italicized for the vector, okay, of theta 1, theta 2. That's the only thing that's interesting here, maybe. Okay? Then I have the regression function satisfies this linearization, right? So I said, okay, let's do for initial guesses, let's regress 1 over y on 1 over x. And that should give me an estimate of 1 over theta 1 and theta 2 over theta 1. And then I'll just take those estimates and I'll unravel them and I'll get theta 1 and theta 2. Okay. So there's a regression of y, 1 over y and 1 over x, and I get 0.005 for 1 over theta, whatever it was, theta 1, 1 over theta 1. So theta 1 is about 200. Okay? And I get theta, what was it? Theta 1 over theta 2. I can't remember which way it goes. Theta 2 over theta 1 is the 0.000025, which gives me the 0.048 when I undo it. Okay? Now you'll see the author, he starts with this thing. By the way, in reading this in chapter 12, beware that everything is fine up to this point, but then he has some errors on the bottom of page 426. Instead of using the Puromycin regression function, he somehow slips in the exponential one instead. He just throws that in and says, where's that stuff coming from? He's putting the right numbers in for the parameter values, but he's using the wrong function on the bottom of page 426. So there's some typos in the book. Okay? Which he's obviously unaware of. Okay. Because those are kind of bad. But he's got the derivatives on the previous page, 425, where he actually takes the derivatives of the partial derivatives of f with respect to theta 1 and theta 2. So those were simply x over x plus theta 2 and minus theta 1. He forgot it. Yeah, there's this minus theta 1x over theta 2 plus x the quantity squared. Those are the derivatives. So those are going to define my variables. Z1, or I think I call them Z1 and Z2. I hope I didn't. I might have called them Z0 and Z1. I don't know what I did, because when I did it, I have to define my variables. I called them Z0 and Z1. Okay, good enough. Z1 and Z2 might have been a little bit better, but anyway. That's a kind of a minor thing. Okay, I only have two variables then, and I'm not going to have any intercept in this model. Okay? So I take my values, theta 1 and theta 2, which were there. And now, as I was going to point out, the author somehow, in his table on the bottom of page 425, which is what I'm going to construct, I'm going to construct a table on the bottom of page 425. He uses initial data, theta 1 equals 205, theta 2 equals 0.08. Where's he coming with that? Well, that's because some experimenters did use those. We don't know where they got those starting values. He just mentions, I'm going to use those instead. But I'm going to show that I get exactly the same final result with a different starting value, which is the ones obtained by taking this simple transform model. Now, I did want to check that the transform model really is no good. And there it is. This is the original 1 over y and 1 over x. Those are the residuals. And there's the normal probability plot of the residuals. It doesn't look too good. Because, all right, the constant variance isn't constant in the residuals. As I pointed out, moreover, there's a nonlinearity in the residuals. In other words, they're not even mean zero. Okay? They're above the line here in a curved fashion. All right? So there's a bias. They're not mean zero. Okay? In this portion, maybe they're mean zero over here. Okay? I don't have enough data to really know. But then the variance is not constant. Okay? So all the bad things, okay, that you can have. All right. So now let's go ahead and compute this table all out, bottom of page 425, where I go ahead and I take these, here are my formulas, x over x plus theta 2 for the first derivative with respect to theta 1. I should have really called them z1 and z2, but oh well. df d theta 2 is minus theta 1x over x plus theta 2, the quantity squared. Pointed those out. I just go ahead and plug it, and I plug in now theta 2 is the 0.0, whatever it was. Okay, 0.048. Where was it over here? I plug in a theta 2, which is a 0.0484. Okay, and I write out these formulas. The only thing tricky about these formulas if you're doing an Excel worksheet is, of course, which you wouldn't have to do on the final exam, but you would have to do for the practice, okay, would be to make sure to get the dollar signs in when you refer to something right, all right? B12 is the first x value. I just memorized that, okay, because that's easy. It's in the second column or whatever. It was the 12th row or whatever. It was the first x value, so that was coming in because I had to put my x, and my theta 2 was, my initial theta 2 was an A47, but I need to put the dollar signs there using F4, right? F4 key puts those dollar signs in for you. Doesn't don't need any of that. No control shift enter because there's no matrix arrays here. All right. It's just that if I wanted to do A47 and then get the dollar signs, if I put A47, how do I get the dollar signs in? I hit F4. Okay. And that's what I wanted there because I don't want that parameter. I don't want my theta to change when I pull this thing down. Right. Otherwise you get a bunch of undefined division by zeros, blah, blah, blah. Okay, similar thing here. What do I have here? What's K7? Huh? Oh, I made a mistake. Undo this. Because I was thinking I'm doing an equal sign. Let's get out of here. Okay. Anyway, here's another formula. Okay. Here's my A45 because there's a theta 1. All right? Of 0. My initial theta 1 was A45, and so on. So there's some more dollar signs in there. You see that? Okay. Then over here, F of 0. I need to find my initial fit. 2. I just plug in the regression function. So actually, where was my regression function? Here, it was right here, f of x and theta. So I'm using that function here. All right? In my formula with the A45 and A47. Then my E0 is y minus F0. Y is A12. My initial y is A12 because y column is next to the x column. Okay, and I just go ahead and compute my initial errors. And there's my S of theta 0. That's how much the sum is. I actually compute the sum of the squares of the E0s. And this is 1920 here. Now what I'm going to do, I haven't done any, that was just from theta to my initial value. So I didn't have to do any regression if I had just picked initial values. Now I'm going to do my first regression. When I regress E0, this column right here, regress this column on those two variables without intercept. Okay, so you'll see that, well, you can't see me do it. I guess I could do it here on the side. Make sure you understand how that's going to go. You need me to do that? Okay. So what I'm going to do is, let's do it on a different sheet. Oh, no, I can't do that. But anyway, I can put the output on a different sheet. I'm going to take these guys. Well, what? Let's do data analysis. What? Tools. Okay, data analysis. Running out of time here. That's what. Okay, regression. Okay. I'm going to take this E0 column and I'm going to regress it on these two columns right here. These two Z's. Alright? And constant is 0. And labels. Both highlighted. And output range new worksheet because I want to put it on a new worksheet. And I'm not going to even bother with the residuals here. Okay? Okay. There's my information. Mainly what I want to do is get these numbers. The coefficients are 15 and 0.0129. Those are increments now to my old thetas. My old thetas were 195 and 0.048. Now these are the increments to those. That's all I want from there. All the rest of the stuff you can ignore pretty much from this calculation. It's just those two numbers, all right, that I want. That's the theory here. So now I go back to sheet 1 and see what I've done here. I took those two numbers, there they are. All right. And now I'm updating my thetas. I took my old theta, which was 845, and I added K37 to it. So I'm not going to pull anything down. I don't actually need to have the dollar signs here. But there's K37. That's K37. My new theta 1. And so there's no intercept here, all that junk, because I did no thing. I'm calling this beta 0, by the way. And the author calls these increment numbers the betas. So he's calling theta, the next iterate is theta plus beta. So he's calling the beta. He just has to have a notation for the increments. He's calling them betas. I didn't need that in my previous thing. I called them coef, remember? He didn't like coef 0, coef 1, coef 2, so he called it beta 0, beta 1, beta 2. All right? And so he's got the vector parameters theta instead of beta. So the betas is now the increment business. But they're playing the same role that we did before, in some sense. It's coefficients of some regression. But now it's residual regression. I'm regressing the residuals, okay, of the fit. Not of the linear fit, but of this nonlinear fit. Okay? And so then I just go ahead and plug those in, and I get some new z's now. So here I wrote z0, z1 again, but of course I have to sub the new theta values in. So now it's not A45, it's J43, or it's not A47, it's J43 for the theta 2. Okay, and now it's not what it was before, but J41 and J43 for my theta 1 and theta 2. So then I get new z's. All right, I get new F fitted values. And new nonlinear errors, okay? I mean, errors from the nonlinear fits, okay? Now S theta 1 is smaller, it's 1200. Before it was 1900, okay? So the fit is better, okay? Sum of squared errors is smaller, okay? I actually never did a sum of squared. I don't really have a linear model, so I don't have anything to compare those with, okay? I have a linear transform model, okay? But that's different units. Okay, these are the original units. Okay, and now I go ahead and get regress E1 again on those two. We're regressing the E1 on those two. That's the key thing here. That unifies all these things together. And to get now update the things. Now I got 212 and 0.0638 and so on. He's following, and now I do a third time and a fourth time. There's only a couple things more to see. When do I quit? Well, now I do it a third time. I update and I put my Z0 and Z1 and I get my E2 and all that business again. By the way, since there's no intercept, I'm getting 12 total sum of squares, 10 residual, and 2 regression. Okay? Because there's no constant. So SST is not the same. It's just a summation of the YI squareds. All right? That's your 12. So your SST should be the same in every, well, not for here, because these SS refer to what? The errors. Okay? So that's looking kind of weird, right? Why does he have negative SS here? So you see, this is not linear regression. Okay? Well, what is it? How can I get a negative SS there? What is this junk? What is going on there? Okay. Anyway, we'll do one more iteration. So a little bit, some unfamiliar things are happening here. Okay? That looks something fishy about that. I don't know what's going on there. I'll have to think about that. What's happening is that because the coefficients are getting, the increments to the coefficients are getting smaller and smaller, that's good. That means it's converging. That means I'm not going to change the coefficient anymore. And so, likewise, the predicted outputs from this regression are going to 0. Because those would be this coefficient times the first variable, Z0, plus this coefficient times Z1, right? So these should be close to 0. So this column should be going to zeros. And these residuals, therefore, should be about the same as they were as the E0 column. Or E1, I'm sorry, the last E column, all right? Because these are about 0. And you're regressing, so you, okay, so then the last thing, I think, I do it one more time saying, okay, this is it. And it really did converge pretty good. these are all these predicted values are about 0, and these residuals are almost exactly the same as they were before. And I got my SS theta is 1195.45. These are exactly the same results as in the book. Okay? Okay. So I get my final business, and I want some pictures to make sure it's okay. So I actually look at E3, right? The last error vector I got. And I plot them versus the fit F3. Okay? And then it looks okay. Right? Errors look okay. And what about the normal probability plot? I actually put that in too. And that looks okay. Yeah, there's one kind of outlier corresponding to this one up here that's a little bit big over here. Okay, so a moderate outlier perhaps. Okay, as you can see, it's kind of hard to pick that because see how steep this curve is right here? So there's an outlier. So it's hard to pick that up. Okay, so it's natural to have something kind of fishy right there. But I think this model performed pretty well. In fact, you can actually go ahead and do an F-test. It's not your standard one. It's not on this picture. It's on your slide there. But we'll discuss that next time. Okay? There's a little bit more in this chapter I would like to just rehash. But then you basically do 3 or 4 regressions and you get your answers. Any comments? Looks like a piece of cake, huh? Go home and do 12.8. Okay.
I didn't get a new thing.
Oh, yeah. Let me give it to you.